Hello, today I'm going to show you how to use table R to identify and name organic functional groups. So we're in our organic unit. Remember, organic is a study of anything that contains carbon, and we care so much about it because every living thing on this earth is made of carbon. It is the backbone of living things. We've spent the first couple of days focusing on hydrocarbons, which are the simplest organic molecules. They're just hydrogen and carbon. And we learned a couple days ago how to use reference table P and Q to name them. So just real quick as a reminder, the name is broken up into three parts. You have a prefix is the most important, that tells you how many carbons, a suffix that tells you what kind of bonding it has, and then a location number, if necessary, to tell you where to put the bonding. So in this case, hex meant 6 carbons. The ine table Q tells you that ine means it has a triple bond, and then that 2 tells you to put it in the second location. And we also learned how to fill in the hydrogens so that every carbon has 4 bonds. That was the basics of that last lesson. So the thing with hydrocarbons is they're a little bit boring. Not like too boring. Hopefully those videos were a tiny bit interesting, but hydrocarbons are mainly used for fuel, like propane, 3 carbons, single bond. That's what's in our gas stoves and our grills. And then butane, 4 carbon chains, that's what they put in lighters. And gasoline is supposed to be a high octane fuel. Octane is just the perfect length, 8 carbon chains, release the most energy the easiest. So that's basically it for the alkanes. Alkenes and alkynes, the double and triple bonds, they're slightly more interesting. Those double and triple bonds make them a bit more reactive. And so you can do chemical reactions where you like add things to them, synthesis reactions, or in organic they're called addition reactions, but you can turn kind of a plain hydrocarbon with a double bond into a bromo halide or something, or you can even make alcohol, but we'll get to that in just a second. So before we move on, I want to show you the skeletal model. Because organic molecules can get very, very large, because we're talking about biological molecules that are just huge, hundreds or thousands of atoms even. Chemists developed a way of drawing these structures that's like the simplest way possible. So I'm really sad we're not in school for this unit, because we would have been building models that look like this. It would have been fun, maybe frustrating for some of you, but probably more fun. So if you were to build octane, that'd be 8 carbon atoms and all single bonds. And then these little white things, those are all the hydrogens attached to them. So you have an 8 carbon chain. And when you actually build the structure, it turns out that the carbons in the backbone make this zigzag shape. So what chemists developed was a way of drawing these structures called the skeletal model, where you just show the carbon skeleton. So if you look, that zigzag for the backbone, that's this right here. This is like the simplest drawing of octane that chemists will draw. And the idea is there's a carbon atom at the end of each line. So carbon atom here, carbon atom here, carbon atom here, carbon atom here. And you don't bother to draw the hydrogen atoms. Like a drawing like this is from one chemist to another chemist. They're like assuming you are a competent chemist. You understand that when I draw this squiggle, it's really like a shortcut for writing all this. Like you and I both know where the hydrogens go. So I'm not going to tell you. I'm going to draw just the most basic structure. So for example, so another example down here, you have 1 hexene. Hex means 1, 2, 3, 4, 5, 6 carbons. Ene means there's going to be a double bond in the first position. And so the way they show that in the skeletal model is just with 2 lines like this. So there's still a carbon at the end here, a carbon here, carbon, 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 and they'll just put 2 lines. And then a triple bond would just be 3 lines. And once again, they developed this method because they needed a way to talk about, for example, hemoglobin. And this is like a small example. Hemoglobin, this is the part of it. Hemoglobin is the protein in your blood that actually carries the oxygen. And this is the heme portion of it. So at the center of it is a little iron atom, and that's what grabs onto the oxygen and carries it to the rest of your body. But surrounding it, you know, there's this massive structure. And you'll notice this is not just a hydrocarbon. I see a nitrogen, I see some oxygens, but I also see all these lines. And so as chemists, we know that at every corner, there's a carbon, there's a carbon, there's a carbon. There's also hydrogens, but they're not shown here. And this is about as simple as you can get. When I was doing my research in college, I was working with organometallic catalysts, and diagrams like this were like a common thing. This is a starting material, and you can do different reactions to make these different products. And so it just gets very complicated very quickly. And this looks complicated, but imagine if we were to draw all the carbons, all the hydrogens. Anyway, I think that's interesting, and it'll make the next slides more understandable. Okay, but before we get there, key thing for today is we are done with hydrocarbons. We're going to start to get more interesting. You're going to see molecules that have functional groups. Functional groups contain oxygen mostly, but also nitrogen and the halogens. And this opens up the amount of reactions they can do wide open, and they can do all sorts of interesting reactions. The regents would say they give molecules characteristic physical and chemical properties, like acids taste sour, or esters smell really good, stuff like that. So we're going to be using reference table R. We'll still use table P for the prefixes, but if we see an oxygen or a nitrogen or something, we're going to use table R, organic functional groups. So just for example, some things where we're not just carbon and hydrogen anymore. The acid that's in vinegar, ethanoic acid, looks like this. And if you, you'll notice we have a piece of it that's not just carbon and hydrogen. We have a carbon double bonded to an oxygen, and that same carbon is also single bonded to an oxygen with a hydrogen, which if we look on here, that's the same thing as this organic acid. So the way this table works, you have like the name of the class, like we have alcohols, we have ethers, aldehyde, ketone, organic acids, etc. And then probably the two most important sections are this functional group and then also the examples. And we'll get to how we'll use those in just a second. All right, so vinegar has a functional group. Here's a structure for cinnamon. So here we got that, that skeletal formula again. So we have a ring made out of 6 carbons and some double bonds. We've got, remember, there's carbons here at all the corners. They're just too lazy to draw them. And then over here, we have a C double bonded to an O and another O, and then a C next to it. This is called an ester, and esters generally smell and taste pretty good. And here's one more. This is caffeine in coffee and soda and stuff. And once again, there's anywhere where you just see an intersection of lines, there's a carbon, but there's also nitrogen atoms and carbons double bonded to oxygen. And so as soon as you add in oxygen, nitrogen, and other stuff, they get a lot more interesting. So today we're going to focus on just 3 of them because we can't be together in person. So I'm doing the simple version of this. By the end of today, I want you to be able to see a structure like this, be able to use table R to write the name. Table P and table R. So how do you name this? Step 1, identify the functional group and find it on table R. So the way we do it is we find the thing on here that's not just carbon and hydrogen. In this case, there's an oxygen. And that oxygen is double bonded to a carbon. And then I'll usually also check what else is that carbon connected to. So it's connected to another carbon on that side and another carbon on that side. So then I go to table R and I find, where do I see double bonded oxygens? None of these are double bonded. I see multiple double bondeds here. So then the question is, which one is the one that we have? So we can eliminate these two down here, organic acid and ester, because they have two O's and we don't have two O's. So it's either an aldehyde or a ketone. Now, if you'll notice the difference, the aldehyde has a carbon double bonded to an oxygen, but also single bonded to a hydrogen, whereas the ketone doesn't have the hydrogen. Now, if you want to, on your copy of the reference tables, anywhere that you see a line with nothing on the other side, you can write a C there. It's assumed that basically always when there's nothing else there, there's going to be another carbon. And that would be a good reminder if you wanted to write on your own reference tables. So in this case, I see, okay, this looks like a ketone. I've got a C double bonded to an O, and even though they don't write it, there's carbons on either side. So I figured it out. It's a ketone. How do I write the name of a ketone? So we are going to look over here at the example. We're going to steal their example, and then we're going to change the parts that we need to, the prefix and the location number. So I'm going to steal 2-pentanone. No. Okay. So the reference table says 2-pentanone. And this name, just like before, is broken up into parts. You have a suffix. In this case, that unknown comes from the fact that it's a ketone, but it still has that prefix that tells me the number of carbons and a location number. So I'll take what it says on the table and just change it to match mine. In my case, I don't have 5 carbons. My ketone only has 3 carbons. So I would go back to table P and be like, oh, 3 carbons, the prefix is prop. So instead of 2-pentanone, this is 2-propanone. And then let's check, is my location number, is this on the second carbon? 1, 2, yes. Done. That's it. I think the hard part is identifying it. But then once you've figured out whether it's an alcohol or an acid, or in this case, a ketone, the rest of it's easy because you're just copying off the table and changing the part that you need to. So let's do another example. So that's a ketone. It has a double bond O with carbons on either side. So in this next example, first I'm going to identify my functional group. So this is normal hydrocarbon. This is the part here. I've got a C single bonded to an oxygen and a hydrogen, and then carbons on either side. So on table R, all of these have double bonds. So if you look up here at alcohol, this has a single bond to an oxygen and hydrogen. Now they don't draw it because once again, chemists are lazy, but it's assumed when you see O and H together like this, there's a bond between them that they're just not writing because they're lazy. So when we see in this drawing COH, all single bonds, that matches the alcohol. So this is an alcohol. I'm going to steal this name and just change the parts that I need to. So the example is 1-propanol. Prop meant 3 carbons in the example. In the example, they used prop because there's 1, 2, 3 carbons. We don't have 3 carbons. We have 1, 2, 3, 4, 5, 6. Prefix for 6 is the same as the prefix for 6 in math class. It is hex. So I'm going to change this to hex. And then I need to also change my location number because this OH is not on the first carbon. It's on the 1, 2, 3, third carbon. And it actually matters because if this OH was over here on the first carbon, it would have a different boiling point. When it reacted, it would make different products. Like it matters whether it's on the first, second, or third carbon. So that's another thing. If the example on table R has a location number, you should have a location number too. All right, let's do one more. I think this is getting a little long. Sorry. Hopefully it's helpful. All right, last one. I see 3 carbons, and I also see a C double bonded to an O, and then also a single bond to an OH. This looks a lot like the vinegar, actually. I think this is the vinegar. So we go to table R, and right here, the organic acid, it's got a C double bond to an O, single bond to an OH. Be careful, it looks a lot like the ester, C double bond to an O, single bond to an O, but in this case, for an ester, it's not an H on the other side, it would be another carbon. So just be careful with that. But ours is an OH, so it's an organic acid. So the name, the example over here is propanoic acid because they have 1, 2, 3 carbons. We don't have, oh, do we have 3 carbons? 1, 2, 3. Yes, we do. Great. If it was 2, yeah, we're good. We don't have to change anything. Isn't that nice? Okay, so I hope that made sense. You're going to have a table of probably about 10 of these, and your job is going to be to identify the functional group and find it on table R, and then use the example to name it, but just change the prefix and the location number as you need to. I hope this was helpful. Let me know if you have any questions. Have a great day.